Okay, so welcome to the afternoon session. I'm Natalie Rowe from Lawrence Berkeley Lab. And I do have a small anecdote to share about Stan, or really about his family. So I was a graduate student here at Stanford. I came in the early 80s from, I had spent a year at CERN working for Carlo Rubbia, and before that I was an undergraduate working for him at Harvard. And I never took a course from Stan, I never worked for him, but Harvard contacted recent alumni asking, would we interview candidates who are applying for undergraduate slots at Harvard? So I rather foolishly agreed. And one of the candidates who was applying to Harvard was, I believe it was Susan Wojcicki. And that's right. Thank you, Esther. And of course, I knew she must be related to Professor Wojcicki, although I didn't know him well. And she was, of course, a brilliant, lovely young lady. And one of the interview questions was, you know, what have you done with your summers during your high school years? And she talked about all the wonderful family trips they'd done all over the world and all the wonderful activities they did together as a family. And I just remember thinking, I'd like to be adopted by that family. And of course, I think she went on to Harvard, and the rest is history. But anyway, it's really my pleasure to be here today for this symposium and to introduce the first afternoon session. So our first speaker will be Karol Lang from UT Austin, and he is going to tell us the story of A Few in a Trillion, a search for rare Kaon decays by BNL E871.
Well, thank you very much, Natalie. So it's my privilege to be here. Thank you very much for the invitation and this opportunity to reminisce a little bit. Stan and I were born in the same city, Warsaw, Warszawa. So I thought that because our native languages were the same, I thought I would actually teach you how to pronounce it properly in Polish. So the name should be pronounced Stanisław Jerzy Wojcicki. And it was transliterated into Stan George. The other thing that I heard yesterday very interestingly is that the grandkids called Stan Dziadzia. My grandkids call me Dziadek. So it's a little bit different, but it's the same meaning. Anyways, I met Stan in 1982 at Fermilab when I was a graduate student at the University of Rochester working on search for the neutrino oscillations in a narrowband beam using two detectors. After graduating and getting my first postdoc at Stanford, I worked on E140 and U141. For those of you who are in the know, may recall these are deep inelastic scattering and an axion search. And I took my second postdoc. I was offered a second postdoc with the group G to work with Stan on the BNL E791. So this was 1986, November 1, 1986 to be specific. I will tell you later that E79 that I was hired to work on first had a long history of turning into another experiment, 871, and this will be really the focus of what I say. But in between, we actually conducted yet another experiment called E88, and in fact, there are people whose lives depended on that experiment, right in the audience here. So at the end of E871 at Brookhaven, I returned to neutrinos at Fermilab, and I joined MINOS in 1995, right after the proposal was actually written. So I continuously worked or collaborated with Stan since November 1, 1986. Just a tidbit. So title of my talk is A Few in a Trillion, and I'm basing my slides on a talk that I gave quarter century ago. This is, as I say, we're going down the memory lane. So it will be a biased, abbreviated story about the search for Kaon decays at BNL, and specifically experiment 871. That the program that spanned the years that you see on this page between 1983 and 1996, and the fuzzy starts and fuzzy exits of this, as you may later see from the dates of the publications. This was Brookhaven back then, and you can probably hardly tell how different it is nowadays. But our experiment was in this B5 line and in this big experimental hall, and the beam was extracted from AGS and ran down here in a straight line to our experiment. At that time, there was a whole industry, Kaon industry at Brookhaven and beyond, because there was an experiment at Fermilab, there were experiments at CERN and KEK, and there's a lot of alphabet soups here that I will not be spending much time on, but all these experiments were essentially looking for new processes in the rare decays of Kaon, and different biases, different experimental tastes dictated people going different ways. And one of them was, I think, maybe returning to Stan's taste that we learned from Jonathan today from End Station B. So 791 and 871 pursued the search for K long to mu E, and explicitly delta L of 2 violation, and also suppressed modes of K long to mu mu, the famous Jim mechanism, and further suppressed by helicity the KL to mu to E. The physics motivation was, maybe still would be if you were to conduct such an experiment, to respond to the fact that we know that the standard model is not complete, that there are many ideas how to extend this. However, because they're well motivated, that the theory can be has to be more complete. And there were lots of papers back then that, in fact, I was amazed that I believe Susan yesterday mentioned Technicolor and left-right. Well, she mentioned Technicolor. I'm forgetting which one. In addition, she mentioned. But there were lots of papers, and there are some examples of papers of theories that were proposing processes beyond the standard model. So, in a classic way, and it's not working anymore.
It's weird. Okay.
It's moving. Okay, so in a classic example, sort of dimensional argument that one would make is that if you were to compare the standard model decay, the K, so-called K mu 2, K plus mu 2, to a hypothetical K to mu E, you can assume a similar structure of the interaction, except maybe the coupling constants would be different, the intermediate bosons would be different, and you can construct this very simple argument that if you were to see such a process, the observation at the level of 10 to minus 12 would produce a limit, or would be sensitive to the energy scale of 220 tera-electron volts. In this box below, I'm showing the limit that was achieved by experiment that we started early on, and that I will tell you only about the continuation of the experiment. So this was experiment. I don't know. I have to be.
Mind-boggling too. There.
Yeah. There was an experiment that we started with in 80. I didn't actually start it, but there was some. I joined this experiment E791 that ultimately achieved a limit on this process of 3.3 times 10 to minus 11. So this was BNL 791, and that corresponded to 92 telectronovolts. So huge mass scales that are being probed by reaching to the low branching factions limits. The standard motivations for experiments improving on KL2 mu mu or KL2 EE were what you would do nowadays with any rare decays. You either improve the measurement of the standard model, or through the precision of the standard model decays, you look for discrepancy, as Andre was earlier saying. Is there anything that we're missing, and thus we're not producing the numbers that theory was calculating? So KL to mu mu, the famous Jim decay, is dominated by the intermediate two-photon interaction, and there are additional terms, not obviously the very important ones, so-called box and penguin diagrams, which show this ultimate suppression. So there were good ways to check the calculations if you can conduct a very precise experiment. Similarly, to EE, KL2E, it's further suppressed by the helicity argument, and there are some differences in what's expected in terms of exact amplitudes for these processes. So generally, the idea is look for K mu E, and at the same time, because this is dilepton state, final state, you need to be reconstructed muons, you need to be reconstructing electrons. You may as well look for EE or mu mu, and precision measurements on these decays gives you sensitivity to probe further the existing physics. That was the idea. Technology.
It's the keyboard.
No, that's. I don't even know what to do.
It doesn't advance. This is my computer. I promise that yes.
It's an Italian computer.
It's yeah. Yes.
Now to
I can sit here. You stay there. Next one.
no, I'm doing it now.
Okay.
Thank you, Jordan. So the measurement principle is. Sorry. Now I'm gonna unwind my talk. Since you are looking at rare decays, it means we have to sift through many decays. Many decays imply that you need to be running very intense beams so that you can sift through many decays. And that implies that there's lots of decays happening per unit time in a very relatively limited volume. So there's backgrounds that are coming from simple overlays or accidental pileups, and in addition to physics backgrounds that I can in a moment, and misidentification. Identifying muons and electrons is easy, but if you do it in very high intensity beam, it's becoming challenging. And since we're talking about low branching factions, everything becomes very challenging. So we had to design a spectrometer that is as massless as possible and as precise as possible in order to probe into these stellar territory. The idea is very simple. You essentially reconstruct two bodies in the final state. You reconstruct the vertex where it came from and its kinematical quantities through measuring the momenta and trajectories in magnetic fields that are downstream, and then plot everything as a function of Kaon reconstructed invariant mass and PT squared of the final state. So very simple principle, and this is where the signal would be, and everything else in that plane would be coming from either physics or background processes of various sorts. So as I mentioned, the 791 experiment run between 83 and 89. So I came sort of in the middle of it. We built very important pieces of apparatus, debugged everything. And it was a very nice first run, but we fell short of the original goals of the experiment. So as I mentioned, I'll come back to this outline of this detector, but I'm just pointing out that it took more than one take essentially to reach the goals that people really wanted originally for this kind of research. So from this experiment, we learned three things. You need better rejection of background, you need higher acceptance, and you need higher rates, even higher than was run earlier. Stan, I'm reminding you, this is more or less where SSC was happening. I mean, it was exactly when SSC was happening, as Maury was telling us. So Stan proposed two new and radical ideas for achieving at least some of this improvement. A beam stop, and that needed our R&D, and upstream straw drift chambers, which also needed an R&D. So this is sort of maybe a nicer look at the spectrometer that had the following sections. So this is where the kaons were decaying. This is, by the way, protons were coming here. They were at small angle, striking target. Only neutrals were allowed to propagate further. And in this tank, kaons were decaying. And downstream of the vacuum window that is permeating this decay volume were drift chambers, magnet, drift chambers, magnet, drift chambers, and then particle identification devices. So there was a lead glass, a Cherenkov counter, and muon rangefinder. So this is all, this largest part of the detector was actually to get the range of muons to within about 5%. I should probably spend a little bit more time on this. All of this was running very hot beam. So this was at that time the most intense beam, proton beam that was available. It was running 1.5 times to the 13 protons every second, and we were running in so-called slow spill. So it took us about a second of extraction. And it was about 10 to the 8 kaons per spill. And unlike in the electron beam, here we did have a lot of neutrons, and they were hurting us. We knew that. And the trigger levels that we were running were so high that we needed several levels of trigger to actually be able to write something to tape. Because back then we were writing to tape. So this is the apparatus that we were effectively the same as 791, but for 871, for next experiment, I want to return to my slide here. The necessary additions were, this is in the first magnet, the beam stop. So this is the gray portion. And these chambers, 1, 2, 3, 4, 1, 2, 3, 4, were the fast drift chambers made out of straws. Now, this is the collaboration that worked on 871, and there are several members here of that collaboration, so you can ask them some details. Essentially, this was a collaboration of Texas, Irvine, Stanford, and College of William and Mary, and Phil Rubin was sort of moving around a little bit. So let me talk about the beam stop. This was a radical idea. I think people were thinking initially, this is a crazy idea. Because you're putting something that is in the middle of the detector, middle of the first magnet, you're striking a very intense beam that can produce anything around it through interaction, high energy interactions. So how do you absorb and thermalize all the neutrons and photons or gammas that are emerging from it. So it took actually a lot of thought, and Stan was absolutely essential in providing guidance how to assemble it all together. So this is left, or I will accelerate. So we conducted a lot of simulations and a lot of measurements in situ with various additional detectors, and essentially agreed that within a factor of 2, we think it would work. So we proceeded with this detector, with this beam stop, and this is one of the graduate students who was happily assembling this together, and this is what it looks like. I want to point out, as you saw maybe on the previous slide, this has a long list of fairly sophisticated metals that we put in together to basically do 2 things: absorb neutrons, thermalize neutrons, and absorb photons, gammas, so that nothing would emerge. So the net effect would be, maybe we have a lot of rate in this vicinity, but downstream it would be lower rate and thus better efficiency for identification detectors, particle identification detectors. So this is a trial assembly of this detector. It started, the core of it was, by the way, heavy metal, the tungsten. And we inserted them into the magnet. And so this is our magnet in which it was inserted. This right photograph is the magnet, and the pointer is not working anymore. And things look promising. So then let me switch to straw chambers. When Stan suggested let's build straws, I think 99% of the collaboration didn't know what he was talking about. And I was intrigued. So we did a lot of ultimately R&D and build straw chambers that were operating on 2 principles. The segmentation was much smaller, factor of 2, and we were operating high drift velocity gas, so-called tetrafluoromethane with ethane, that allowed us to sample high intensity decays. So this is basically what's behind these pictures. Straws required a lot of R&D, so, and we did this. I moved back then. I was lured to go to Texas, so I did go to Texas, and all of these pictures come from my first lab operations in Texas. These were basically 1 by 1 meter chambers, and there was about 7,000 channels altogether. And this is the crew of my students, and I want to point out an engineer that I learned a lot from, Marek Hamela, who came from Warsaw. Now, this is where the chamber went into. So these are the stations where the chambers were placed. This is a vacuum window. This is the first magnet. And this is a different view of the downstream window, which had to be very thin because it needed to be minimal amount of material on the way of decaying kaons. As you know, so I'm giving here I'm showing you here some pictures of people who are not even here, unfortunately. Casey's though here, and if you ever worked at Brookhaven, you would know that these guys, riggers, dictated what you were doing. So we were at their mercy, but things worked out. The chambers were rigged in. We were working on electronics. This is another of my graduate students, and Casey working on electronics. Stanford actually undertook the design of the front-end electronics, and you see it here in somewhat poor rendering, but that's the best I have. And we ran into all kinds of issues. We discovered on the first trial run that our gas system was actually full of, or not full, but it had sulfur in it, specifically SO2, that was activated in the radiation and essentially was eating up the copper on the straws. That's why you see these dark streaks were coming from essentially copper being eaten by the gas system. So we improved that. We knew what to do with the gas system. The chambers worked very nicely. They had very good resolution, very sufficient efficiency, which was essential. And the rates that we're running here, so this is the beam stop, the rates of the upstream chambers was up to, close to 1 megahertz per wire. While as you see, these downstream chambers dropped in the intensity. Thus, we were able to better operate the particle identification. And next to the last day of 1995 run, so this was our first run. There were 2 years of running, 22 weeks and 22 weeks. People called me, and from Fermilab, I was in Austin, and they said, "You will be disappointed." It turned out that the downstream vacuum would have imploded, and essentially sucked in the upstream chambers completely. They were completely destroyed. So you see here some of them, and I flew to Brookhaven, and Stan flew there as well shortly after then, and we met with this chap whom everybody knows, who Mel Schwartz by then has returned to High-Energy Physics and became the BNL HEP director, and he graciously supported the reconstruction of the straw system. So we were given essentially all the funds that we needed. The time was so precious and very crucial in meeting the deadline to essentially reconstruct the system for the next run. We had basically 7 or 8 months to do so, and the entire collaboration pitched in together and had done that. So at the end, we reconstructed the system even in better shape because we decided to build new straws out of not mylar but Kapton. For various reasons, it's actually a better solution. We improved our analysis by pioneering the so-called blind analysis, essentially by peeling off region by region and simulating what we would be looking at in the next region. And ultimately, when we looked into the box area, that was actually the shape of this box was achieved to maximize the acceptance and transitivity of the experiment. We found no candidates, and we're able to set the limit of 4.7 times 10⁻12, few in a trillion. For muons, k long to mu, we found about 7,000 very clean events, and measured the branching fraction with best resolution so far. And we were peeling off with the electrons the same way, and by peeling off, we actually discovered that there are 4 events. And there are fairly undisputably K long to EE that had never been observed before. And with this observation, we set the branching fraction to the number you see here. And this is, to my knowledge, still the rarest decay ever observed in particle physics. These events were very, what one would say, vanilla-like. They were sampling the distributions in a very expected way, and we're convinced that they are really very legitimate. There's nothing that points to their background, and this is the end of the road that we have seen so far in decades of these explorations. In 2011, 10. We celebrated Stan's retirement. We have come here, and this is a group photo of many people from that era who were engaged in this experiment. Some of them are in the audience again. So let me just say that we have pioneered instrumentation and analysis. We have overcome many challenges due to natural physics processes and man-made calamities. I did not mention several other calamities that happened to us. And I think that it's very safe to say that without Stan's intellectual and personal leadership, we wouldn't have succeeded. Okay. I would stop here, except I have one more slide because it's related to straws. So as I was developing, we were developing instrumentation. Somebody suggested, why don't you think of using straws for registering photons or gammas? Specifically, we built not out of straws because these are now aluminum tubes, but the same technology otherwise. We built what we called the xenon straw PET scanner, very tiny. This is 0.5 centimeter each straw. And it didn't go anywhere, and I can tell you other stories related to it, which are quite ugly, but that's life. But 25 years later, I've returned to PET system, and we now built with completely different technology. It has nothing to do with straws, but we now built a LISO-based and silicon PM's system, which is positive emission tomography as a feedback to proton therapy. And not only that, as many of you perhaps know, there's this new effect called flash effect that nobody understands. We actually conducted very novel experiments where we actually took some of these elements and exposed them to flash beam at MD Anderson and published 2 papers. This is the first one. This is published in June, and this is the highest downloadable number of highest downloads paper since June in physics, in medicine and biology. And this is really among my personal spin-offs of this beautiful venture with straws and rare decays. And I'll thank you here.
All right, thank you, Karol. So this session is open for questions. Yes, Georgia.
What is this flash thing? Sorry, because I'm ignorant now. So
Oh, you should invite me to give a long talk.
yeah, maybe we will.
So
Let's see what.
just so very short version. Over the last few years, people discovered that delivering about between 40 and 150 grays per fraction of a second spares healthy tissues, leads to lower toxicity of healthy tissues, yet eradicating cancer equally effectively. And it's something that is not understood. So if you Google flash effect, your Google will flash out with all kinds of ideas, all kinds of conferences and talks and whatnot, because this is the hottest topic in radiation oncology. And we have the only instrument that can actually probe it. And NIH just rejected my proposal 2 days ago.
Any other questions or comments? Yes, Bill.
Yeah, I can make a comment. I mean, we've heard a lot about how Stan is unflappable and, calm in the face of, difficulties. And Karol mentioned, one such difficulty where we had an implosion of a vacuum window, which is totally due to Brookhaven engineers not understanding the properties of Kevlar. And that's partly, I guess, why Mel decided that it was on their back to pay for the replacement. There was another disaster, which, lesser people might have walked away from the experiment at that point, where over some holiday, I forget which one it was, we came back and we found that part of this beam stop that was constructed, the outer part of it was copper sheets, some, I don't know, 1 ton or 2 tons of copper. And somebody, unknown to this date, and decided that they wanted that copper. And the only way to get the copper was to put it through the straw chambers.
No, drift chambers.
The drift chambers that
Your drift chambers.
my drift chambers. And that was the way to get the copper out. And so they destroyed the drift chambers. We had to rebuild those as well. And the funny part of the story was we had collaborators from Texas, and nobody can trust Texans, of course, especially Texans who drive pickup trucks. And so the FBI came, and they were very interested in talking to a particular Texas graduate student who drove a pickup truck to see if that person was responsible for the theft of the copper. So throughout all of this, Stan was, completely level, and we survived these things. The other comment I'd make is, Stan on the beam stop, when we were trying to decide how to upgrade E791, there were a couple of ideas. I had one, Stan had this one, and I was not a big fan of Stan's idea. I didn't think it was going to work, but we eventually decided to do it. And it was very imaginative. For example, if you want the highest hydrogen density to absorb neutrons, it turns out the highest hydrogen density material is zirconium hydride. It's zirconium with 4 hydrogens. And so not only is it much denser than paraffin to absorb the high energy, but it will also absorb neutrons or degrade the energy of neutrons by interacting with the protons. I don't know where he figured out that zirconium hydride was the highest hydrogen density, but he would do things like that in very imaginative ways of finding and imaginative ideas of putting this beam stop absorbing and the 10 neutrons per second, or some very large number of 10 GeV neutrons or 7 GeV neutrons right in the middle of an experiment, and it worked.
Was the copper radioactive when it was stolen?
Probably slightly radioactive.
Probably not that much, because this was at the very beginning of our assembly of the beam stop.
Did they find it? Was it the
No.
Texas grad student?
No, it was negative found. No, the grad student, it was in Texas somewhere.
Just get it from catalytic converters.
Well, thank you for those anecdotes. These rare decay experiments are really tough, and particularly tough when you have to overcome all these issues. So let's thank Karol again for